Good afternoon, everyone. It's a pleasure to have Professor, Stefano with us today. Professor Stefano is an IEEE fellow. He's also a member of the Royal Holland Society of Sciences. Also an ERC laureate, and he has done a lot of exciting work. Leading a large group in diverse fields, ranging from manipulation to having birds which fly, robotic birds that fly. And I think one of his, you know, recent or maybe for a long time interest is how do we bring in physics and robotics together, which has also led to, I hear, explorations in quantum, more recently. So, I mean, I do feel that there is this notion of embodied AI where people try to use AI developed for the virtual world and plug it into robots and say, we are done. But that's a very misrepresentative perspective in many ways. And I'm looking forward to the insights that Stefano is going to bring forth. So please welcome Stefano again, and looking forward to your talk.
Thank you very much. So first of all, it's a great pleasure and honor to be here, to be invited. I spent some time with Neville many years ago, and I have very, very good memories at MIT. So what I first will tell you where I'm coming from. I'm coming from the Netherlands. If you cut my arms, you get Italian blood, but I actually live in the Netherlands for 35 years. And I live, the university is right there, it's very close to Germany. And our university, you don't probably know, but it's, I think in Europe, the most entrepreneurial university of Europe. Maybe ETH and Twente are about the same. But Booking.com, you may not know, but it's actually from Twente. Takeaway.com is another unicorn from Twente. Companies I've been involved with Demcon. For example, our group created Demcon, which is the main mechatronic delivery for ASML in the Netherlands, who makes all the most important chip manufacturer in the world, and is now 1,000 people, I think. And Clearfile Solution, I will say something about it. And then my last company is Magnet Medical Robotic, which is actually, we have an office in London and one in the Netherlands. And it has very serious investment, and you will hear more about it in a year or so. My group, which I have the pleasure to lead, is called RAM. Robotics and Mechatronics was a control group, which I let it grow to a reasonably large group. It's about 70, 60 people. And we have also some, for the medical application, some surgeon in part-time working in the lab. And it's a very synergetical group. That's the way I try to work with the group. We work on many different things, from domain independent to domain dependent stuff, technology they can use, or theoretical and very practical. And today, I will actually be on the theoretical side most of the time to tell you, actually a tutorial-like seminar. So let me give you the motivation of what I'm going to talk about. Robots are a physical system. Well, it was just said, that many people forget about that. But what a robot is a physical device that interacts with the world. Okay. Energy is the mathematical embodiment, okay, of the invariance of physical laws. And I will come back to that later. I mean, this energy, of course, was historically speaking started, from a concept that was done by engineering thermodynamics, but we found out that there are mathematical reasons why energy is there. And physical interaction of robots with humans is the core of robotics, I would say. Okay? And mathematics is the most powerful tools that engineers have in order to do things, innovative things. And yet, most of the time, energy is completely ignored in many robotics applications. And physics and mathematics is not taken seriously. And what I want to do in this talk is give you an idea about a concept which has been driving my complete career, which is port-based concepts, port-based ideas. When I heard it for the first time, moving to the Netherlands as a young graduate, and working with Peter Breedveld, who actually spent also time here at MIT working with Neville, I just didn't get the point. Okay, and then up to the point that I got the point, and I cannot think otherwise since then. So I've been working along this line with port-based things. These are some of the things I've been working on. And I think there are a lot of ideas that we had discussion about some of these things before. But I will not talk about this. If you're interested to know more, I can, of course, discuss this issue. But I want to start with a game. So you know what this is. This is called a dovetail, right? Is a connection. So you have a red part and you have a gray part. And if you buy an IKEA or a lot of stuff, you basically have these two things that can shift. Rigid bodies have 6 degrees of freedom with respect to each other. You basically fix 5 and you give 1 free to a nest, and then you block it, done. Can this move with respect to each other? Can the red and the gray move with respect to each other? Who's for no? Who's for yes? A lot of people don't dare. Well, the point is, of course, I want to trick you, and there is no problem. Okay? There is no problem whatsoever. Okay, they can move. Are there other solutions? Of course, it's symmetric. There is a discrete symmetry diagonal on the other side, but are there more than those? Now I trick you once, you start thinking, right? And the point is, there are many. There are infinite solutions that actually, this is one, and there is another one, and then I will stop. So why am I showing you this? Well, I think very often when we work with stuff, we learn things in a certain way, and we just are blind of other ways of thinking. And this is something which is, something we should be as scientists, as engineers, be very much aware. So I will try to give you, at least to trigger you to think about and look at a port-based way of thinking, because it is a different way than you may be used to it, which has incredible potential. I'm working now, as was mentioned, with a theoretical physicist on gravity and quantum, and with Friedrich Schüller, superstar of differential geometry. You may know the guy. He moved from Erlangen to Twente. We are working together now. He was blown away by this way of thinking. He said, how is it possible physics do not use this concept? So it's not stupid. And it was actually started here at MIT, by the way. Aristotle said, in all things of nature, there is something of the marvelous. And being an Italian, of course, I cannot avoid to cite Leonardo da Vinci, right? So Leonardo himself started studying birds and making this design. And of course, Leonardo is an example, I think, to us all. Okay. So in this talk, I want to tell you what port-based thinking is, talk about the project of the bird, and give you actually a primer on exterior calculus. You say, what is this? Well, this is the way you should have learned integration at the first place. It is absolutely ununderstandable that in every university in the world, you learn integration using Riemann, which is a very, very old way of thinking, which completely hides a lot of stuff. I'll try to explain it later. OK, so let me give you an introduction. You may know these two guys, do you? Mythbusters. So actually, all started this issue of flying started in a collaboration that I was doing with especially Jamie, so the guy with the head like that, because we wanted to try to build a machine that's actually a flapping machine that it could fly with wings, together with other activities. And then this bird was actually initially done by a falconer, and then we got into the game, and we improved it, and it did a lot of stuff. And this is unique in the world. It flies at up to 80 kilometers an hour in 504 wind, has the same size as the peregrine falcon, has the same flapping frequency of the peregrine falcon, the same weight. And we got a number of awards, the Tech Transfer Award, we got Best Paper Award, the cover of the Robotics and Automation magazine. And I want to show you a video of this thing. But before that, how does it work? So hypothesis is that when you flap, if you have a steady flow of an airplane, okay, you have steady flows, and you want to avoid to have stall, right? Because if you have a detachment of the fluid, you have a problem. But birds actually do it continuously to fly, because they invert, as you see here down there, they basically shed these vortices in a certain way, and then by doing that, they create thrust, and basically that's the way it flies. So, but I was triggered, like, it works, but why? Why and how does it really work? Okay, do we understand the physics? Because if we don't, we cannot improve it. We can just hack. But you know, I'm an engineer by training, but I want to do science. Don't want to hack. I want to understand things. And as Ludwig Wittgenstein, you may know this, is mathematician and philosopher from Austria, he said, what we cannot speak about clearly, we must pass over in silence. And unfortunately, nowadays, we are surrounded by people that never heard about this. Okay, so to talk about robotic flapping clearly, we must use the right language tools. And I have reason to believe, and now certainly because I did it, that port-based is the way to go. So I will kind of work in two ways. So I will kind of concentrate on, you know, Aristotle divided knowledge, epistemology, in techne and episteme. Techne is more the engineering work, the building stuff. And episteme is more the, you know, conceptual science that's connected to, in the Enlightenment, more to René Descartes, for example, instead of to John Locke and Aristotle himself. And I will start with more the conceptual side. We have the bird, and we can decompose it, right? When we have a problem in engineering, we decompose it in smaller parts we can understand. We know how rigid body works, right? Because we have a body of the bird, and you have two elastic wings. And as long as you want to describe the interconnection of the wings with the main body, you know, we can use what you see there, SE3 are Lie algebras, which means basically twist and wrench it, force and velocity, just for the time being, that you can pair them in a way I'll show you later, but we know that. We know how to do these things properly. But things get very nasty if we have a wing, which is a nonlinear elastic deformable body, who's actually moving in a fluid, who's described by Navier-Stokes equations, which are two PDEs, both nonlinear, and they interact through a layer, which is the surface of the wing, which actually moves. You know, when you study PDE, you basically take the beam, you fix one beam on one side, and that's as far as you get. We're talking here about 3D PDEs interacting with each other on a boundary which is dynamics by itself. Pretty nasty. I think that you cannot define a problem which is nastier than this in classical physics. And we actually nailed it. And then but you need to understand how to model this in a way which is completely coordinate invariant, and I'll tell you what that means. So let me first give you an idea of the project.
Nature is amazing, and birds are amazing creatures. But we do not fully understand yet how they can fly. Could we really understand the magic of flapping flight so that we can build robots that can fly better than the robots that are currently available? The Robird is the only robotic bird in the world which can fly in up to 5 Beaufort wind and at a speed of 80 kilometers an hour. It weighs the same as a peregrine falcon, and it looks like it, but do we really understand the underlying physics? We believe that flapping flight is achieved with a combination of flapping and twisting of the wings, which creates detached vortices which generate thrust. But are we at the moment using the optimal combination of the oscillatory pitching and plunging motions of the wing? To answer this question, an experimental setup is built in the wind tunnel of the University of Twente to see how the wing moves and how the stream of air moves around the wing while it's flapping. This allows for exploring the optimal wing motion for the Robird. A helium-filled soap bubble generator is installed which blows thousands of bubbles per second into the wind tunnel. 4 high-speed cameras film the bubbles to capture the movement of air around the wing with the shedding of vortices. Furthermore, a force sensor at the root of the wing can measure the resulting forces on the wing, like lift and thrust, and reflective markers on the wing can be filmed with cameras to track the wing movement and deformation at a sub-millimeter scale. We have studied the flexibility of the wing since it's an important part of why the Robird flies the way it does. Different than many people think, intelligence can also be embodied in the material and properties. A brain without a proper body is useless for locomotion. We want to bring this physical intelligence in the wings of a robotic bird, and in order to do so, we created smart wing designs and smart mechanisms which are able to change the mechanical stiffness of the wings to change the flying behavior. But But how can we precisely describe the physics of a robotic bird with deformable wings interacting with the air around it? The unique feature of the approach we followed to describe dynamical physical systems is that it relies on energy and geometry. Energy is probably the most fundamental concept unifying the various branches of physics and explaining how nature works. In the Portwings project, we used the Port-Hamiltonian framework to get insight into the energetic fundamentals and transport phenomena of fluid dynamics, structural dynamics, and fluid structure interactions. In the Port-Hamiltonian framework, we describe any complex physical system as a network of energetic modules interconnected using power ports that characterize the energy flow within the system or exchanged with the environment. For example, if we consider the flapping wing setup we developed, we describe it as a network that represents the dynamics of the driving mechanism, the elastodynamics of the wing, and the aerodynamics of the air around it. The power supplied from the power source flows to the electric motor, and then some of it is stored as kinetic energy in the mechanism's inertia. Some of it is dissipated as heat and noise, and the rest goes to the flexible wing. The power supplied from the wind tunnel is also transferred to the wing through the moving boundary of the wing and the airflow injected inside the wind tunnel. In each cycle of the wing's flapping, the power supplied to the wing oscillates between kinetic energy and elastic potential energy, while the power that flows to the air is either stored as kinetic energy or dissipated in the vortices formed due to the wing's flapping motion. Our Port-Hamiltonian description of this physical system differs significantly from the standard approach of continuum mechanics using coordinate-based tensor calculus treatments. We rely instead on coordinate-free exterior calculus and describe the network structure of the system using so-called Stokes-Dirac structures. This methodology allows us to intrinsically handle open boundary conditions and thus use, reuse, and combine submodels in such a way that a real Lego of physics would be possible. Consequently, this leads to the development of structure-preserving computational algorithms that allow us to efficiently and robustly simulate these physical systems to produce predictive computer models of the world around us. The real advancements in science and technology are only achieved with a deep understanding of the fundamental theory, as well as proper engineering and experimental skills targeted to the goal to be achieved.
I'm very happy and thankful. So this is give an overview, and I hope to show you some of the tools that we've been using. But before doing that, I like games. And I want to make the point that mathematics is not useless, okay? So do you know what matrices are? You said, yes. Well, let's see after this game. Do you know these two guys? John Feynman, okay? One of the biggest minds ever lived. He created the computer on one side. He did all the mathematics to do quantum mechanics, okay? And he was a student of the other guy. He worked with David Hilbert. You may have heard this name, I hope, okay? So he did all the functional analysis, and Emmy Noether and other people. I mean, these are two of the big geniuses of the previous century. And then, they know mathematics, and we give two matrices, 2 by 2 matrices, and we ask some questions to both. And we say, take the square of this matrix. So John Feynman calculates it. And David Hilbert says, it's not defined. I can't do that. And you say, what? Well, he's right. He's absolutely right. They are both right. But they have, the color of the matrix is different. So what's going on? Then he asked to calculate the inverse. And John Feynman calculated the inverse. And David Hilbert does calculate the inverse, but he changes the color. Interesting. And then we asked John Feynman, is your matrix symmetric? It's impossible to answer. He cannot say that, and he's right. You start getting confused, right? So you thought you knew what matrices were, huh? But they're both right, actually. I'll tell you why later. And David Hilbert say, oh, no, I take the transpose. They are different, so it's not symmetric. Calculate the eigenvalues. And John Feynman tells, OK, the eigenvalues -3 and 5. And David Hilbert, who's not stupid and knows matrices, says, it's not defined. I cannot calculate the eigenvalues. And the determinant, well, your eigenvalue, no problem. And David Hilbert, I told you, it's not defined. I cannot talk about eigenvalues of this matrix. Do you know what's going on? Very likely you don't, and many mathematicians don't. But this is one of the basic things of mathematics. If I tell you how the base change of this matrix, does it start ring a bell? Not yet. Well, let me tell you what the reason is behind, and I will not spend much time, but just to show you that it is important to understand things. A matrix is just a representation of a linear operator in the first case. If it's a linear operator, and you go from V to V, taking the square of the matrix, it goes from V to V, and from V to V. You multiply the two matrices, so that is not a problem. But if the matrix is a quadratic form, it's not a map from V to V. It's a map from V to something which is called the dual, which represent, for example, in physics, okay, in robotics, V would be velocities, and V star would be forces, belong to two different spaces. So if I map from V to V star, I cannot use a map that goes from V to V star again. I can't. Makes no sense. Because it's not defined from V star to V, but it's from V to V star. So you cannot take the square. If I take the inverse of this map, okay, and from a map that goes from V to V, the inverse goes from V to V. So it's the same color. But if it goes from V to V star, the inverse goes from V star to V. So it's a different kind of map. The transpose, you can calculate it. But if you have, on the other hand, you want to invert the indices, it makes no sense, because if you have a quadratic form, like kinetic energy, you multiply on the right and on the left for V. So you could kind of look at the other way around. It makes sense. But a linear operator, you can't. It's not defined. Okay. And eigenvalues, the way they are defined, can only be calculated for linear operator, not for quadratic form. There are papers written and published that calculate eigenvalues of inertia matrix. It's nonsense. It's complete nonsense, et cetera, et cetera. So here I just want to show you that even a concept simple as a matrix, matrix are not mathematical objects, okay? These are examples of things that you have in robotics which is just wrong. Manipulability, it's a wrong concept, the way it is defined normally. Not all the time, because Jacobian is a kind of map that goes from a vector space to the vector space. The transpose Jacobian is not the same thing, so you cannot start from V. You need to start from the star. I can tell you if you're interested after the lecture, I can give you more answer on that. As I say this, you cannot calculate. Stiffness is also a concept which is very often wrongly used, excuse me. And this has more subtle reason on differential geometry. So to make a long story short, coordinates are a curse in science. And engineers also should understand what it means to talk about physics, because as engineers, we talk about physics very often. We should be able to understand the physics without coordinates. Coordinates is an artifact that we use, okay, in order to make calculations, okay? Matrices are not mathematical objects. It has been known for years. 99% of books have fairy tales written on it, which is actually books which should be used for different things that to be read. I will not tell you what. And you know what this sentence means? Nullius in verba is Latin, of course. It means don't take anybody's words for it. Okay? So if I tell you something, trust me. You should not trust me in academia. If I tell you as a professor something, you should not trust me. I should convince you that what I'm saying is right. And this is the basic of a good academic education. And this is written in the symbol of the oldest scientific society in the world, the Royal Society of England. Okay. So, mathematics is not there for nothing. And what I want to tell you now, to use this concept to try to give you an idea how to understand this bird stuff by realizing that coordinates, you should be careful about coordinates. Okay. All right. So first, a glimpse of what kind of problems that we've been solving. You know what who's this guy is? René Descartes. Okay. That's the guy who actually gave you the Cartesian coordinates. But he did not only do that, which is very useful, by the way. It's very useful. But is the guy who actually, in Enlightenment, gave us the way that if we have a complex problem, we want to decompose it, understand the parts, and then recompose it. This way of thinking is actually coming from this guy. Okay. So the first thing we wanted to do is says, how do you model a fluid in a completely open boundary way, okay, but then completely agnostic from the coordinates you use, and possibly a fluid on a sphere like it's used in meteorology. Okay, and we did that. We published this paper with completely open boundary. Yeah? So you have a PDE with boundaries which can be varied. Okay. Then we worked on advection, because if you have a fluid, the fluid can move around energy or other stuff. And we published another paper on this. Then we said, all right, now we understand what a fluid is without dissipation. But of course, that's not air. Air has dissipation. Fourier-Navier-Stokes, the difference between Euler fluid and Fourier-Navier-Stokes is that you have dissipation. How do you handle that? Okay. And also including bulk and shear viscosity. And then we published 2 papers in the Physics of Fluids. That's the major journal for this kind of stuff. And also about the advection. And we looked at thermodynamics in fluid in a very different way. And then was the core. It says, good, now we know how to handle this fluid stuff. But how can we handle the fluid stuff with moving boundaries? Okay, we have a PDE with moving boundaries. And this was this paper, which was a big achievement, I think, in the whole project. And then, of course, this is great because from a conceptual point of view. But you want to do, for example, control or optimization. So if I have PDEs, which are, written in mathematics, what can you do with that? Well, it turns out that if you do the math right, you will have methods of discretization which outperform anything out there. You may know ANSYS is another package that is used all over the world, a multi-billion company, right? Well, our system, ANSYS, if you mesh something too small, it will not be stable. Our thing will always be stable because you give the mesh and we'll give you the best physics possible that match that mesh. And then we look at elasticity, nonlinear elasticity, and we published a number of things on elasticities. And there is this library, by the way, PyM, you can check, they explain some of the numerics related to this. So what is pore-based things in a pore Hamiltonian system? Well, it started all here, actually. Harry Painter had the vision, the genius to understand that when you talk about interconnections of physical systems, then you need to talk about ports. And that is fundamental in robotics, because if you have a robot which interacts with the environment, that's what you should talk about. That's a port that interact 2 systems. But that was the core idea, the pioneering idea, which has then been lifted to a more sound mathematics by Bernard and Arya, with whom I've worked regularly, and I will see them next week, by the way. They brought this to a real sound system theoretical approach. And I brought all this stuff to robotics myself. And this has to do with university. Well, I put this slide just because, MIT is a leading institution in the world. And I think that I really am, in the years I'm thinking about education more and more. And I think that we should rethink education, because we can do a bit of linear algebra and then something in mechanics, in electromagnetism, in fluid dynamics. I'm absolutely convinced by now that if we had a curricula which would give proper linear algebra and basic concept of differential geometry, not a lot of math and understandable stuff, basic concept of differential geometry, and then a good course on port-based modeling, you could use electromagnetism, mechanics, fluid dynamics, even quantum mechanics as an example. Because this idea of port is so fundamental, so spread out, that you will, in the same time, understand that all the physical domains are all the same, actually. So, who this lady is? Emmy Noether, okay? David Hilbert and Albert Einstein said there was the most important woman in the history of mathematics. She never got tenure because she was a woman, okay? Thanks God, things have changed. And there were people that, big scientists that were ashamed that a person of this caliber didn't get tenure just because she was a woman. She did the impossible. But one thing I will notice is Newton's theorem in physics tells you that if there is a symmetry, there is a conserved quantity. And that is why the reasons why energy is there. If physical laws do not change in time, and that's what we call a physical law, then immediately implies that there is a quantity which we happen to call energy, which is conserved. And Albert Einstein said that all the branches of physics and all the law will be seen again. But thermodynamics, which is a subject which, when I was a student, I didn't appreciate the importance of, okay, is the core of everything, but will never change. And this is exactly the basis. So energy and power is the glue of all the branches of physics. And so when we do modeling of physical kind of system, we want to use this. And in physics, Hamiltonian systems are used, but Hamiltonian systems have a number of drawbacks because they are top-down, and instead what I'm talking about is really more the physics, be able to interconnect things easier, okay? And it does not have anything of the restriction that Hamiltonian system theory has. Port-based thinking, port-based Hamiltonian system, it's really a lingua franca which allows to do all multi-physical modeling you could imagine. And I will use two figures to make a point of what I will discuss. This guy, Cantor, you may have heard about Cantor in set theory. He did what is called a naive set theory, which is Bernard Russell found out that was a problem, okay? But he basically also did something about infinity mathematics. And there was a big crisis in the 1900s, which kind of created two groups, what were called the intuitionists and the formalists. And these are two guys, Poincaré was a more representative of intuitionist, and David Hilbert was a formalist. And I will use these two pictures to talk about two things which are very important, which is duality and the inner product. And that is something that is mixed all the time. And if you mix it together, you will never solve big problems, as I'm finding out right now with quantum physics. So what is duality in mathematics? Okay. So if I give you a vector space, what is a vector space? Well, it's a set with two operations that you could do things with, okay? And you can choose a base of a finite dimensional vector spaces, okay? And then there is another thing, which is a dual vector space, which is the space of linear operators from that vector space to a real number. What are you talking about? Think about physics in mechanics. Velocities are vectors. Forces are linear operators from vectors to power. That's the right way of looking at it, because forces are different things. Forces are linear operators from velocities, to power, okay? And they have a different base. It's a different space. So you cannot use the same base. It's a different base, okay? This is completely ignored in 99% of the book of linear algebra. It's unbelievable because the consequences are huge, okay? And then if you want to apply one of the other, you get this, you can use dual bases in a certain way, okay? And then if you have a vector, it's a linear combination of the element of the bases, and also a dual vector is the linear combination of the element of the base, as you do all the time. But notice that here, these columns are numbers, and these are real vectors, elements, abstract element, and this is the other way around. And then you get something which is called, and that is something quantum mechanics, forget it, covariant and contravariant. Because these things, if you change coordinate differently. And that is the core of the reason why you need to make a distinction between these two objects. So the bottom line here is vectors and covectors are different things. Okay, forces and velocity belong to two different spaces, mathematically speaking. Okay. Okay, forget about this. So velocity and twists, for example, in mechanics are vectors, and forces and wrenches are covectors. And many of the mistakes that have been published in the literature in robotics, but in other fields as well, are actually based on this simple distinction. Okay, and if you haven't understood the distinction, I could explain it later, but it's not a difficult thing to eventually understand. Why don't people use it? So if now, what is pairing? If I give you now two elements, two sets, and I want to return a real numbers. So if one is a vector, one is a covector, velocity and the force, we know how to do it. You don't need anything else. You just say a force is by definition a linear operator from velocity to power, so you can give me a real number, which we call power, right? You can just apply the efforts on the flow. In this case, E and F would be velocity forces and velocities. But then now I give you two vectors, two velocities. Can you return a number? In general, you can't without any other structure. Because you need something which takes two vectors and return a real number. And that's called a Hilbert structure, an inner product. An inertia matrix kind of stuff, are two different objects. And this, I will connect this to, let's say, the Hilbert structure, inner product, to the standard duality, which needs no extra structure. And this is the core of something that is messed up all the time. The difference between topology and geometry. If I give you a sphere and an ellipsoid, they are the same object, topologically speaking. There is no difference. Actually, they are the same as a cup, because I can take a rubber sphere and deform it and make a cup out of it. I do not punch it. I do not change the topology. They are the same thing. But if I give you distances of points, then you are talking about geometry. You see, topology is something which needs less structure. There is no information about distance, all right? And there is a relation between the two. You know, one of the biggest problems in topology, the Poincaré conjecture actually was proven by using what is called the Ricci flow, which connects the two, but that's a different story. But topology is connected, in my things, to Poincaré, and geometry is connected to David Hilbert. Okay, now we get to the point. If I give you a system, and I want to decompose the system, and I want to talk about a physical system. We said energy is the glue of everything. So if I want to decompose, what I would like to have is to say, okay, I decompose it in two parts. And if I had that the system initially had a certain energy, if I decompose, I want that the energy is preserved. That's my conserved quantity. So whatever happens, if energy goes down here, it should go up on the other side and the other way around. Otherwise, energy would be lost. You know, first principle thermodynamics does not allow that. Okay, so how do you describe this? Well, we want that the power transfer is conserved, so how can we do this? Well, another thing we know in physics is action reaction. So you cannot have that, if you have interaction of two physical systems, that one of the two systems sets everything. You cannot do that, because that would mean that that system can generate energy as much as it wants, because it's independent on the other side. So for physical reasons, if two systems interact like a robot and a human being or whatever else, there's always a bidirectional interactions. This is unescapable. So what is the nature of these things that I called E and F mathematically? What are they? Well, it turns out that now you understand, because actually are vector space and the dual of vector space, like the force and the velocity. You see, now in order to talk about power, I don't need anything else. I say, okay, if a robot and a human interact, they will interact with the forces and velocities. Okay, and the dual power, the pairing, which is natural, will give you the power that exchange. And if you have a robotic hands, you will have more parts, more forces and velocities, but it's all the same. Well, it turns out that this is more general than this. So this is actually true for any kind of physical domain you could ever imagine. Fluidodynamics, continuous dynamics, everything. This is a very universal concept. So in the case of electrical circuits, you know, voltages and currents are just scalars, that's easy. In the case of multi-body dynamics, you have what is called the Lie algebra here, are the twists and the wrenches. If you go to infinite dimensional system, nothing changes, just the mathematics gets a bit more complicated. So the question is, what are vectors and what are covectors, which is V star, for the cases in which you're talking about distributed systems? Because fluidodynamics is a distributed system. Okay? It's a field, what is called a field. In each point is a different value. Okay? And this is the notation that Henry Painter here at MIT introduced for bond graphs at those times. Now, geometry is, you know what this painting is? This is a famous painting of Raffaello you can find in the Vatican, okay? And he represents Plato's Academy, okay? And in Plato's Academy, at the entrance in Greece of Plato's Academy, there was written, Agiometriso mediasicito. So he said, let no one ignorant of geometry enter. Because for the Greek, geometry and mathematics were a kind of representation of intellectual capabilities, okay? And in the case, so that's why it's so important to think about topology and geometry and make the distinction when it's there. So how can he lift this to fields for the bird, okay? How can we do that? Well, you need to go to fields and to define this duality in fields. And the question, how are you going to do it? And I will try to give you at least a glimpse of how to do it, because, of course, we will need more time. But I will try to to trigger you in trying to understand and abstract on the main concepts and the reason why you may be looking at this. So we have our wings. Have you seen the video before? So the boundary is, for example, the surface of the wing. And then you have a system, which is the fluid around it. And then you have the elasticity inside the wing, right? So, but I want, and of course, the wings can deform, become curved. So you need a way to describe this all in a very general context, okay? So you have a manifold. Manifold basically is space, a nonlinear space. And then you have that the boundaries, this is the symbol that mathematics is used to define a boundary of a space. The boundary of the fluid is the same as the boundary of the elastic elements, okay? That's where the ports is used to interact between the two. And my goal was to have it working not only in 3D, in ND. Because if you understand it in ND, then you can use it 3D as an example. And if you go, for example, as I'm doing now to relativity, you need 4D, for example. You want it coordinate-free. Why? For the reason I told you about the matrices. If you use coordinates, you may draw to conclusions, which may be depending on the coordinate you choose when you don't even realize. Okay? And applicable to all physics domains, possibly curved. And the way to do it is a part of mathematics, which should be basically taught to all engineers as long as I'm concerned, which is called external calculus. External calculus is not new. It's been there for 100 years. Grossman and Cartan introduced it. And that is the way, actually, what integration is. And yet, as I said before, we teach to our students Riemann integration, which is very bad. Lebesgue integration is better, but we don't teach differential forms. So what are differential forms? So what are differential forms? Just think about a multilinear operator. What does that mean? Suppose a matrix. I give you a matrix, right? If I give you a matrix, you can multiply it on two sides, and you get a real number. And if that matrix is skew-symmetric, because you can't talk about skew symmetry, so it's antisymmetric, that would be a two form, because that's two sides. You can apply two vectors. If I give you a cubic matrix, okay, if a cubic matrix, you could multiply it on three sides. That's a three form. And of course, you cannot see it, but I could give 20 dimension, right? But it's linear on each of the arguments. And whatever you invert these two arguments, you get a minus sign. That's it. That's what a form is in numerical representation. And it's a field. So this matrix changes in each point. Here's a certain value. Here's another value. Here's another value. Here's another value. And what a zero form is just a function. This function at a certain point. And integration is nothing else than pairing a domain, okay, with this object, which is a form. If I give you a function on this space, you know what it means to say, give me the value of that function here. You give me a number, right? Or give me the value of the function here. I could generalize this and say, give me the value of a one form on this curve. And you give me a number. Because a curve is a one-dimensional space, right? A surface is a two-dimensional space. So you can pair these objects to generalize it from function to higher dimensional things. And this is what integration is. Has no metric structure whatsoever. You always write dx when you integrate. And you think that there is a Euclidean structure. It's bullshit. It's not right. It's not true. Okay? So it's a generalization of a zero form you're integrating on a point. You basically value that on a point. A one form is on a line. A two form on a surface. A three form on a three volume, et cetera, et cetera. Okay? It's the generalization of evaluation of a point. And then you can be more precise because you can also have, and this is also, a lot of people using this math do not realize this. If I give you a curve, you can orient the curve, right? You can walk like this, or you can walk in the opposite direction. And there is something about orientation which is fundamental in physics. If you talk about the flux, it does matter if the flux goes this way or the other way. So there is something, forget about this definition, but there is something that describes this also in details, okay? And then, and this is the core, there are three operations in these objects, in this algebra. There are three operations. The first operation is called a wedge, and you have seen it maybe when you did integration. You do dx wedge dy when you do a two-order integration. That's that wedge. That's that wedge. And what it does, if I give you a k-form, what is a k-form again? Something that you can integrate on a k-dimensional thing. So instead of one form is integrated on a line, two form integrated on a surface. And I give you an L form, whatever L is. The wedge creates something that integrates on a K plus L. So if I give you, for example, two one forms, one form, you take the wedge, you get a two form, you can integrate it on a plane, okay, on a surface. That's the first object. And then you have another thing, which is called the D. I've seen a D before. Yes, that's the D you always use. Okay, if you have a coordinates, you take dx, that's that D. But that D can do much more than what you thought. Because this is the generalization of Stokes' theorem in all possible dimensions. I don't know if you did fluid dynamics and electromagnetism, of continuous mechanics, all this calculus of, gradient, divergence, rotational stuff, it's all that D in this setting. It's one object, it does everything, and every dimension. Instead, the gradient and all the other stuff that we use and is still taught instead of this stuff, which actually introduced by Maxwell at the end of 1800, and we are still using that. Meanwhile, there's much more powerful stuff to learn. Amazing. And then there is a third object, which is called the Hodge, which basically says, okay, if I give you, and by the way, the D increases of 1. Okay, if I give you something you can integrate on a line, you take the D, you can integrate it on a plane. For example, coordinates, x. The coordinates is a function, right? If I point a coordinate. If you take dx, integrate it on that coordinates. You see, it's something that you have already used before. And these things is something that complements the dimension. So if I give you a K form on an n-dimensional space, the Hodge would give you an n minus k. What does it mean? Suppose we're in 3D, fluid dynamics. And I give you a one form, the Hodge of one form should be a do form. So if I give you something that can be integrated on a line, the Hodge would give me something that you can integrate on the plane. Okay? This is very abstract. But there are just these three things that play with these objects, which I call exterior calculus. The bottom line is that thanks to this Hodge, I then have an inner product of this field. So like, in vectors, I give you a matrix, and I multiply right and left, and I give you a real number. Now instead of, I have an infinite dimensional vectors, which is called a field. And if I have a one form, I have two one forms, I have a machine, if I give you this extra structure, to give me energy, for example, for a field. Okay. But if I give you a K form, and then n minus K form, okay, I can take the wedge, what do you get? You get an n form, which you can integrate on an n volume. So you see, here is the duality. This is the V star that I used before in finite dimensional. You can generalize it to something which is actually a field. Okay, that's the bottom line. Here you need nothing else for the ports, and there you need an inner product in order to do that. Okay, it turns out, I will skip the details, it turns out that all these things you may have seen if you have done any continuous calculus, okay, it's, as I said, something which is very old, only work in 3 dimensions, cannot be generalized, is not able to talk about many of the things we needed for the bird, okay? But if you generalize this to this and eventually to what these complex are, what is this? Well, these are all forms. These are 0 forms. If you take the D, you get a 1 form. If you take a D, you get a 2 form. If you take a D, you get a 3 form. It doesn't stop at 3. It can go to any dimension, okay? And what is the Hodge? You see, always the dimension the other side. So if I give you a 3 form, okay, in 3 dimensions, n minus 3 is a 0 form, is a function. Okay? This is really the geometry of proper exterior calculus, which the vector calculus we usually learn actually is just a bad way of doing. And it turns out, and this is the clue, that you can perfectly discriminate orientation. What is a form? What is a pseudoform? But the crucial thing is that what you could not do before, now you can disentangle topology. The D is something which is completely independent of metrical structure of space to geometry, which is that. And this seems like, now why would you care? Well, I don't have the time to go in details, but this is the core, the real core, why in a lot of problems in physics, people have not seen what is possible to see in this way. Okay? Maxwell equation, just as an example, if you take electric fields, it is a one form. The magnetic field is a two form. You take the D, you take a two form. If you go to magnetics, for example, okay, it happens to be a one form and a two forms. And then you see that everything I said, these are the Maxwell equation in these settings, and you can, all the mathematics is just absolutely crystal clear. You do not need any assumptions. It's all there. And if you have a question, I can handle it later if you have a question about it. So the bottom line, eventually, is that you can, by using this wedge, define duality. So you can define a port. So if you have this wing, you can define this field on the wing, and it's dual. We would be, for example, the motion of a particle and the pressure distributions, okay, which is what it is in order to transfer power. And you can build all these mathematics, which makes possible what I just said before. I will skip this. Just show you this. You know, this is, again, is a bond where all these things are now fields, are not just vectors, are fields that are defined in all space. And you can generalize this idea of duality to any dimension in any possible situations. And it turns out for nonlinear elasticity, things get even more complicated from a mathematical point of view. And the reasons for that is because in Navier-Stokes and nonlinear elasticity, you have certain effects like shear, which cannot be modeled otherwise. And there are very specific reasons that you immediately understand using this mathematics why that's the case. The good thing is that you can then, if you have these tools now, you understand how to discretize it. You can go to numeric, you can do learning, you can do a lot of the things which very precisely show you how to do it. And we published these things. This is a lecture I gave at the Center of Mathematics in Montpellier. Is a way that it's unique. It's a publication we did in Journal of Computational Physics. And once again, I don't want to bother you on the details, but there is a very, very clear way to describe finite elements. Is anybody working with finite elements? The way you can look at this as a projection of the vectors on another subspace. This is a subspace of the generating function of finite elements, but if you're not working finite elements, it is too abstract. But everything becomes very clear, and if you do it in this way, you have a way to discretize PDE, which outperforms anything out there. ANSYS is going to be burned out. If this thing is going to implement it, ANSYS is out of business, seriously. Okay, and this is what is called structure-preserved discretizations. Okay. Let me get to my conclusions. So this is the way, forget about this. Okay, so in the dual field, as I said, you have a way to discretize that not only in space, but also in time. You know, have you ever heard about symplectic integration? If you want to do, for example, in astronomy, you want to calculate the orbits of a planet in 2,000 years, okay? If you make a small error, of course, things diverge, okay? So you need to be sure that volume is preserved, and this is what is all about, the symplectic integration. So there are things to do this very precisely in open boundary, and this can be used in these settings. On the practical side, as I said, we've been working with elasticity in the wings, how to define change the elasticity in the wing. We have created sensors integrated with printed carbon materials, ink, in order to create sensing within the structure we built. And as it was shown in the video, we have some setup to do all the measurements. These are some of the measurements we are still processing about the videos. And I just want to show you the audio, a last video before concluding.
Working in aviation, waste management, or agriculture, one knows that birds can be of great nuisance. Birds spread diseases.
This is more about the business model of the bird.
The surroundings. Nothing, however, tops the risk of bird strikes in aviation. Clear Flight Solutions has the answer to your problems. The Rollbird. The Rollbird is an environmentally friendly solution for all your bird-related problems. It is a flapping wing robotic bird that not only looks like a bird of prey, but also flies like one. We have many years of experience in unmanned aviation and bird control. Our certified pilots are experts in flying our row-birds. As safety is paramount, our row-birds are equipped with state-of-the-art autopilots, GPS, and geofence systems. We make sure that the pilot in command is always in control. The instinctual behavior of birds when confronted with a predator is flocking together for maximum safety. By flying around the flock, the pilot can remove the birds lastingly in the direction of choice. Shortly after this, birds will start to recognize the area as a territory of prey and will start avoiding it. By mimicking nature, Clear Flight Solutions creates a unique bird control system that birds will never get used to. We make sure your skies stay clear.
A real different kind of video. This was a corporate video, of course. Okay, let me get to my conclusions. I think that, as Albert Einstein said, true knowledge comes with deep understanding of a topic and its inner working. And I think that it is very, there's given not enough attention to this. We learn tricks very often, and we use tricks. But we should ask, as engineers, scientists, as academics, why are these tricks working, and are the best tricks to use? Okay. So I think port-based methods result in in really substantial fundamental contribution in understanding the physics of continua and flapping flights. And of course, it's a complex topic that I could not explain clearly in just one lecture, but at least I hope I triggered your interest in trying to understand this, to probably look at this. And then new tools were needed. So we needed to extend this exterior calculus in a way that we did, and then we could do all the things that I mentioned before. Port-based thinking was the driving force behind all this, and I was very, very sad to hear that Nevels was teaching, and now he's not teaching port-based thinking anymore. And it is just, it's born here, guys. It's born here at MIT. You should learn these things, and you will see more and more in the future, I'm sure. And as I said, I'm this idea showed me that insight on something which is one of the biggest fundamental problems in physics, which is related to quantum field theory, gravity. And this is something that I'm working right now. My personal advice, especially to the PhD students, to conclude. Deeply understanding the right mathematical structure needed to understand the problem, not too much, not too little. If I learned something as an engineer, because I was building stuff since I was a kid, it seems like a mathematician, I build stuff, okay? Is if you use the right structure, okay, then you will be driven by the mathematics. Positions are not vectors. That's a wrong statement. Don't do that, okay? Let the mathematics structure guide you along the way and be critical at each step. And yet, follow the intuition in this adventure. Concluding with my citation, I think that epistemological growth is not about solving a problem, but understand why and how to solve it. Thank you very much.
We have time for a quick question.
Or a phone call. Yes?
Can you say it on the mic, Neville?
Stefano, great talk, as expected.
Thank you.
My understanding is that insect flight is quite different from avian flight.
Sorry, could somebody close the door, please? Yes?
So, insect flight, as far as I know, it's quite different from bird flight. And they have this phenomenon, I think they call it clap and fling, where they bring the wings all the way together and then separate them, generating some. So, have you considered looking at that, and any thoughts on how hard is that problem?
I have the mic. So I think that the fluid dynamics laws are the same. It's just, of course, that is the ratio. When you have frequency, there is 12 numbers that actually is what parameters that basically define certain, how the physics works. And I think that it is substantially different if you have insects. There was here Kevin. Oh, there's Kevin. Who's doing phenomenal work on this stuff. I think that the way that the insect works and a bird is different because of the scale. So insects create downshaft, and this is what, for example, Kevin is looking at. Instead, in these birds, you kind of combine the gliding and the power you generate with this vortex, with the Kármán vortex. So, I mean, the physics is the same. The tools that I developed are general enough to describe all the kind of physics. If the numerics will be done, then we will get to a situation in which you can basically, as we were discussing, you could do learning on this stuff. Then it would become very, very interesting, because you would have numerical methods to do model reductions, which just outperforms anything out there without losing the physics. And that is what I'm so excited. And this is only possible because of the mathematics which is used.
No more questions. Let's thank the speaker once again. So thank you, Stefano, for the talk.